All right, well, welcome everybody to our weekly Wednesday webinar series. For those of you who want continuing education, please watch the entire session. Take the survey. The survey pops up at the end, right when we get done, and/or the survey is emailed out to you an hour later. It's the same survey. Please only take it once. And even if you don't need CEUs, please take that survey. We definitely want your feedback on how we can do better. Thanks to today's first session sponsor, GeoComfort Systems have earth-powered HVAC to help you and your clients get to net zero energy target easily and affordably. Several projects we have worked with these systems have achieved the Zero Energy Capable or ILFI Zero Energy certification using low energy but comfortable HVAC systems provided by GeoComfort. Besides forced air, GeoComfort Systems have an all-new water-to-water system that can power your water heater, radiant, driveway melt, pool, hot tub, and more, all without additional water heating. Bonus, 30% tax deduction is reapproved by Congress and is retroactive for 2017 projects. Make sure you get your system spec'd by the end of this year, 2019, to get that full tax credit, but then tax credits still remain throughout that. Thanks to our session main top tier sponsor, T-Stud. T-Stud is the 2019 Green Builder Media Sustainability Award winner for structural ingenuity. So what is a T-Stud? This T-Stud is a game-changing technology. It solves the #1 nemesis of construction industry, how to cost-effectively stop the transfer of outdoor climatic heat or cold from affecting the interior of a structure's ambient room temperature. Plainer terms, a T-Stud is the best piece of lumber available to minimize the outdoor temperature from coming through all the framing members in a wall to negatively affect your client's heating and cooling bills. It's a thermally broken insulated wall stud assembly for use in exterior walls and party walls. It's an engineered building product that uses 2 lumber members and an internal truss system and a froth-in-place closed cell foam that has a global warming potential of less than 1 and is EPA compliant for 2020. The T-Stud provides a 99% complete thermal break through the wall assembly with just one product. The T-Stud raises the bar on 6 major construction concerns: thermal breaks, structural strength, wind loads, sound transmission, fire safety, mold, termites. It's not complicated. It's quite easy to replace the traditional 2x lumber with T-Stud with little no additional training. Plus, it can be used as studs, jack studs, king studs, sills, cripples, headers, top and bottom plates, and rebates may be available within your state or local utility. All right, well, welcome everybody to From Control Layers to High Performance Enclosures. This course is approved for 1 hour in continuing education units, namely LEED AP Homes, NARI Green, AIBD, Certified Green Professional, and BPI NonWholeHouse, as well as AIA, Health, Welfare, and Safety, which may make it applicable to your state-based design or contractor license. I will be your moderator today. My name is Brett Little, and I am the Executive Director at the nonprofit, the GreenHome Institute. Today we're going to be talking about better walls to stop moisture, save energy, and hopefully save time. And our speaker today, who I'll introduce real quick before handing it off, is Pat Hellman. He's an Associate Extension Professor in Energy and Building Systems with the University of Minnesota's Department of Bioproducts and Biosystems Engineering, and serves as a coordinator of the Cold Climate Housing Program with the University of Minnesota Extension. He's a lead faculty member for the Building Science and Technology undergraduate degree program and a principal investigator for hydrothermal testing. Currently, Pat is a project lead for North Star, one of the Department of Energy Building America's teams. So with that, Pat, I will hand it off to you, and please take it away.
Yeah, good morning, or yeah, for most of you, probably still morning. Excited to be here, and we're going to go through a bit of a background piece, if you will, on control layers and work our way into a case study on 3 different building systems that are out there today that are, let's just say, a novel approach to how the control layers are put into a wall system. I want to start with a little background just on the idea of why we need more robust building enclosure systems in general, but we'll focus primarily today on walls. And then we'll do the discussion about the 4 control layers and the important characteristics and functions of those layers, attributes, etc. Then we'll quickly introduce the perfect wall and go to the case studies. The whole point here is to try to use building science to help us to higher performing, more robust building enclosures. A couple of overarching themes that you'll see here is we're not going to talk about, individual specific products in detail. I think in the past we've probably gotten a bit too hung up on the products, and sometimes we forget to take a look at kind of the bigger picture and embracing a more robust systems approach. Also believe that sometimes the emphasis on finding the perfect product reduces our attention to both design and to the construction process and how important those are to high performance. So I'll open it with just a couple of challenging questions kind of tied into that theme. Is it possible that we've overinvested in products and underinvested in good design and proper execution? And so again, I think sometimes we think things weren't well thought through in the design process. Other cases we have a beautiful design, but they're not executed properly on the job site. The second part of this is also important, I believe, is that are we not being realistic about the construction process or even the operational phase by the homeowner or occupant? So in essence, are we investing in systems that are pretty risky, demand perfect execution, which we know today is a challenge to achieve? Are we counting on perfect homeowner operation and maintenance? So I'm seeing a note here. Are my slides advancing properly?
Not if you have been advancing them, no. We're still on the first slide.
Oh, it's advanced on my screen. So what's going on here?
There we go. Now
Did challenging questions come up?
Now they're up, yep.
Oh, no, I can't. I'm paused. The same note is what I call the growing epidemic, not my jobitis. And one can imagine that there's probably a very expensive machine that does this striping. Someone probably sits behind the wheel and has days or weeks of training on how to use that machine, but a simple oops and we're in trouble. So the whole idea of it's got to be systematic, including execution. I'm assuming we're advancing now, Building America.
You are not advancing any longer, no.
Well, come on. It says pause, then when I go on air, it doesn't want to.
Yep, now it is on Building America. So whatever you're doing now.
Okay, so there was the humor slide. But anyway, let's move on. So I want to just acknowledge we're part of the Department of Energy's Building America teams, bringing housing innovation to market. I just want to borrow a couple slides from them, and I also will make reference to the Zero Energy Home program that they sponsor in a few places throughout today's presentation as well. So the first one is just this reminder of, we can get very hung up on chasing BTUs or kilowatt hours, and just focus so heavily on efficiency that we forget about overall performance. And in the context of a home or a building enclosure is, we need one that's certainly energy efficient going vertically, but we also want one that's high performance, not compromising durability, indoor air quality, not being inconvenient or requiring heroic maintenance efforts, etc. So the point is always, as we try to improve the efficiency of our building enclosures, make sure we're moving to the right, making sure we're trying to go up and over to the top right quadrant there. It's just showing kind of the progression of light bulbs and how in some cases we've taken steps backwards before we go forward again, and we want to avoid that in our building systems and building enclosures in particular. Again, just to mention the Zero Energy Ready Home program and the attributes of that program and the guidance that it provides to try to make sure that we have holistic, system-supported, high-performance buildings. So this idea of robust, it's a word I enjoy using a lot. I think it really conjures up a lot of things about what might be wrong out there. Is sometimes we end up with systems that are not robust. We'll come to that in a second. But the idea of having system materials and systems that are strong, hardy, able to withstand unexpected conditions, sturdy, durable, hard wearing, in a sense, things that just take a licking and keep on ticking, so to speak, using an old Timex commercial. Fragile's the opposite, and I think we see that in the marketplace today, sometimes too frequently, where we have something that is just simply not able to withstand the stresses and strains that are placed on it. Maybe it made perfect sense on paper, but it just ended up being too fickle to handle kind of the rigors of real life, real construction or real operation by occupants. So in the end, when push comes to shove, will your home's response be fragile or robust when we throw things at it like climate extremes or maybe excessive indoor humidity conditions, an execution error on the job site, unusual operations, or perhaps even neglected maintenance? Will it still do its job? So the robust, again, is more of a theoretical construct. Don't think of it as a thing, but more of a way of thinking about whether it's building materials, the design, the systems, the construction, execution, or even operation. In essence, is it idiot-proof, bulletproof, or unlikely to fail? And so far, I've found very few that fall in this category. We all try to strive for that, but it's pretty challenging, especially if we want to keep it within the context of affordability. So the next step is, well, if it does fail, is there a planned backup or redundancy? And we'll be covering that a lot today with the idea of the control errors and drying potential. If it fails, it won't hurt anything else. It's simply harming its own layer or material or whatever, and something that perhaps can be easily repaired or replaced. I'm going to go through the building science review very quickly. I just want to make a couple of key points here. I'm sure most of you are quite familiar with HAM, heat, air, and moisture flow. And just a reminder that heat always flows from hot to cold, or more energy to less, by conduction, convection, radiation. We won't go through those in detail today. The second part of heat flow is that heat moves through the building in two very distinct ways. One is heat flow through the building materials themselves, I'll refer to as transmission losses. It's basically heat transport through our materials by convection, convection, radiation, and that's what we look at as materials having an R value or resistance to this heat transfer. The second way is airflow, where air is simply being moved from inside out or outside in, and in the process carrying its heat with it. So, insulation might stop the first, maybe it'll stop the second, maybe it won't. An air barrier obviously stops the second one, but may not provide that much R value to slow down the first one. Airflow, basically, it's just two key points. To have airflow, you have to have a pathway, a hole. That could be an unintentional hole, it could be an intentional opening or vent. And we have to have a pressure, either natural forces, stack and wind, or mechanical pressures that are induced by mechanical systems to create that pressure and move air across the pathway. On the moisture side, I want to make just a couple of quick observations or points. First is the moisture states, solid, liquid, and vapor. I think we're all pretty comfortable and familiar with that. But I want to add, when something is absorbed with a B by a material, it's typically drawing in liquid water, generally capillary action. We think of a paper towel picking up a wet spot on a countertop. That's absorbing the liquid into the pore structure, into the fibers of the paper towel. Adsorbed is when water vapor molecules are basically adhered to a surface, a pore space, or a cell wall. Some surface is adsorbing these vapor molecules, but it's still not liquid. A quick example of this is if you weighed a piece of paper, dry paper, and then put it in the refrigerator for a bit, or a freezer, and pull it back out, it will actually weigh more. Even though there's never been any condensation or any liquid water, the surfaces have picked up or adsorbed water vapor molecules. Now, again, the weight's going to be change will be very small, but that's just an example of this. It's highly critical that we understand this, though, in terms of material storage and, in particular, safe storage of water vapor within materials. Then the moisture transport mechanisms, we'll go through those quickly again. Most everyone's comfortable with bulk water or gravity water, or water's running downhill, and the whole concept of trying to manage it outside the building, down and out and away. Pressure-driven flows, whether it be wind pressure or hydrostatic pressure that's pushing water at the joints of the building and pushing it into spaces perhaps that we don't want it to be, or the flip side is, if we know that's going to occur, how are we going to take care of that water at a later time? Capillary wicking is wicking of the moisture, liquid moisture, into the pore space of the materials. We're certainly familiar with this with concrete, wood, sand, other porous materials that where the capillary action will draw that liquid against gravity even up into these pores and potentially up into our home. That's the vapor, liquid side. On the vapor side, there's two key transport mechanisms. They're quite unique, quite different. They're somewhat analogous to when I was talking about heat flow or heat transport, both by transmission or air leakage. So the first is vapor can move with airflow. So if we have, again, a transport of a volume of air from one location to another, not only will it carry its heat with it, it will also carry any vapor with it to the new location. And that can be a powerful mechanism for moving vapor from indoors to outdoors, or outdoors to indoors, or indoors into our cavity, etc. The second vapor transport mechanism is diffusion, where vapor pressure, going from a higher vapor pressure to a lower vapor pressure, from more molecules per cubic foot or volume to less, will move across our materials based on their permeance or permeability. And so again, this is a very slow process by which vapor molecules move through our materials from one side of the structure to the other, generally outward in the winter and inward in the summer. I will add though, below grade, and we're going to talk a lot about that today, but in the below grade, the vapor transport direction is always inward. Adds some complexity to that component, but again, for another day. And just comparing vapor transport by diffusion versus air leakage, this is many of you have seen this slide in many, many different ways and different contexts. But the point here is that water vapor diffusion by molecule through a material is a pretty slow process, even for a fairly permeable material, versus airflow through a hole that can carry large quantities of water to a new location. And again, there's a lot of conditions around how this exercise was set up. I'm not going to go through all that. It's just to note that vapor transport by air leakage can be very, very powerful. Vapor transport by diffusion is much, much slower. However, we're going to find out that vapor transport by diffusion is critical in our building materials. It is essentially, as we take away air leakage, which is important for other reasons, the only way to dry materials once they're wet. So we can't kind of just say, well, it doesn't matter. Diffusion is still important in wetting materials, although it's very slow, but it's mostly important in how we dry materials. And finally, there's this moisture balance, the idea of we have wetting happening in some location, we have drying from that location perhaps. Does the wetting exceed the drying and fill the vessel here at the end of our teeter-totter or fulcrum and cause a problem? But it only causes a problem if the safe storage capacity is very small, or vice versa. If we have a large safe storage capacity, like we used to have in, multiple width brick, white brick walls, or masonry wall systems, etc., that had a high storage capacity, they could occur. A lot of wetting and could occur. The drying could be a much further down the road into the future and still survive. So there's just a number of elements here that have to be balanced if we want to have high performance durable walls. So bottom line, over some critical period, drying has to exceed wetting. Material storage provides the buffer between the wetting and drying period. And I won't go through all these details, but I'll just comment on one in particular. If you think about steel framing, for instance, with fiberglass bats, there's essentially no moisture storage potential on either of those products. And so what it's saying is if moisture is moving into those cavity systems, with limited storage, whether it's be by air leakage or by vapor diffusion or by liquid transport. There's just nothing there to safely store that moisture for later removal. On the other hand, heavy masonry materials or heavy wood framing, as we know in the past, could take that on and get rid of it later, again, assuming there was a drying potential, meaning there was energy available and a direction for the vapor to dry. So let's move into really the meat of it today, and that's the 4 control layers. And so I'll go through each of these layers. There'll be an opportunity for some questions and answers on those as we go through, or questions, and I'll try to provide answers. And then we'll move into finally kind of the perfect wall in our case studies. So every enclosure element, and today I'm going to use walls as our primary example here, it needs 4 things: thermal control, water control, air control, and vapor control. Now we can argue all day long what's the right order here. I don't think it's probably appropriate to use a lot of our time to do that. I just want to make the comment that most people would put thermal control last, and in some respects that's probably fair. I'd put it at the top of the list to make a point, and that is if there's no insulation, water control, air control, and vapor control are much less important. There's so much energy flowing through the system that we can get a water leak and it will dry. There's so much air moving through the system that if we have air-driven condensation, will be followed by air-driven drying. If we have vapor that's moving through and it condenses for a period of time, there's energy available to heat it up, evaporate it, and move it on at a future point. So the whole point here is, as we add thermal insulation, the rank changes. The water control, air control, and vapor control become more and more important as we increase the R value. So let's start with thermal control air. I think this should be obvious to everyone. The intent is basically to slow down heat flow from warm to cold. The primary driver is temperature difference. That's generally set by our indoor and outdoor conditions. We can't do much about that. So we simply try to add more and more R value between the 2 boundary conditions to reduce that heat transfer. How much do we need? Where do we need it? What type do we need? You know, in a lot of ways, we've spent decades on these questions, and I think for the most part, we have it pretty well figured out. I'm going to just show some examples here quickly. The first, I have each component, if you will: ceiling, walls, penetration, frame over, ambient, foundation, and slab. And then there's 3 columns representing the Minnesota code. I recognize this is going much broader than Minnesota. That's fine. It just gives a benchmark. The second one is the Zero Energy Ready Home program that I referred to from DOE. And again, it is a performance-based program, but there are certain expectations or metrics here that are kind of set the baseline, if you will. It's basically IECC 2015. So showing for walls, for instance, in R25. And then the last column is net zero energy. There's a great article out there. I have this in my resource list at the end of the talk today. So when folks pull it back up, you can go find these resources, called Zeroing In by Joe Stiebrick. And it's an incredibly deep, dense article, easy to read, but very insightful. And basically what Joe's saying, if you want to go for net zero energy today, based on the cost of renewable energy supplies today, primarily photovoltaics, you're going to want to invest beyond zero energy ready levels to get the loads down under control so you can go with a much smaller renewable energy system. So again, those are just guidelines. I think some good guidelines, by the way, to kind of guide where you're going. Passive house, of course, has levels that are probably at the net zero energy or beyond. And finally, for thermal insulation, I want to remind folks of a technique called the pen test. Don't look at all the detail here and all the writing. That's not the critical piece here. What's critical here is recognizing the layer that is intended to be your thermal control layer. It could be layers. In some cases, it may be multiple materials, multiple layers of materials. And just look for its continuity as you move around the building. So how much roof insulation is there? How much wall insulation is there? What are the windows insulated to, et cetera? Kind of just what we covered. But now it's how are they connected together? Are there areas of considerable thermal bridging, whether it be framing, corners, pillars, structural supports, etc.? And then again, how does that connection occur between the roof and the wall and the window, a wall and the floor slab, etc.? Great technique, and you can use this for any detail. You can use this for a close-up, window detail, a head detail, or a sill detail. You can use it cross sections. You can use it at plan view. It's a very, very powerful technique. Next up is the water control layer. Again, I think it's pretty intuitive what this is all about. The intent is basically to keep liquid water from reaching any moisture susceptible layers or materials. The primary drivers are gravity, wind, capillarity. And the reality is you should take steps to reduce these drivers. Obviously, we should keep water off of our building system as much as we can with good design, overhangs, etc. Our cladding systems should shed the bulk of the water back to the outdoors. We do things to try to reduce the wind pressure or wind-driven rain across our building enclosure system, etc. So that's clearly important. We put capillary breaks in to reduce the ability for capillary wicking between materials or within our building systems. And again, it's this reminder as we remove drying potential, and we're removing drying potential in three really important ways. First, we're adding insulation. Adding insulation reduces heat transport, and that energy is important to keep vapor a vapor, one. Two, that energy is needed to take liquid water, whether it was condensation or a leak, bulk water or capillary water, and warm it up and get it into its vapor state so it can continue on and dry out. And again, we've reduced airflow, so there's less air drying potential. And we've introduced in many of our building systems multiple vapor retarders that are going to slow down, even if there's some energy available, going to slow down the ability for that vapor to move in its natural drying direction. So that's why many would argue, and really I concur, that water control is the most important layer here. I want to remind folks that one of those sources of bulk water, certainly exterior water is what comes to mind for most folks. We have the same situation below grade with groundwater, etc. Condensation that turns into liquid water and starts to move or be transported as liquid water. But we also have liquid water sources on the inside, things that might happen in the future, such as plumbing leaks, spills, overflows, or even liquid water that might occur during an extreme event, let's say a hurricane or something, where there's a breach in the enclosure. So all of those need to be kept in mind as we design our system for managing water. So controlling bulk water is clearly the single most important factor in the construction of robust, durable, and healthy buildings. The highest level principle is to use gravity wherever we can to shed water down and out. Use that to manage both our rain, surface, and groundwater. And in a sense, just drain everything. But the follow-up is, well, we're not going to have perfect control over our bulk water or liquid water from all directions. And so here's kind of the caveat or the backup. What can't be drained has to have a robust backup. In a sense, a leak isn't a leak if it leaks back to the outdoors harmlessly. If it doesn't affect any moisture susceptible materials, it's safely stored for a period of time in a material that's not moisture susceptible, or it is in no way providing an opportunity for mold to grow within the indoor environment that might impact indoor air quality. So there's some exceptions to this rule, if you will, if we understand when these water leaks become problematic. So the backup is, if your first line of defense fails, there could be a second water management layer. There could be a secondary system for water removal, such as venting or active drying, or we could simply build in safe storage with a clear drying potential or drying strategy in days or weeks to follow. Again, the idea of the pencil test is very appropriate for the water control layers. It can identify Again, what material you're using as your primary water control layer, if you have secondary or backup control layers. You can look for continuity at connections. And in particular here, you're going to want to do your pen test, if you will, on some very close-ups like the window head, the window sill, to look for things like your pan flashing detail at the sill of the window and how that carries water out and over, hopefully, your exterior water control layer to where it can be safely removed from the building enclosure. So again, same detail. Continuity here is important. It doesn't have to be perfect, just has to be continuous and lapped in the right manner so that water will in fact run down and out. Third up is our air control layer. And again here, the whole intent, pretty intuitive I think, is we want to stop airflow from moving across our building enclosure. Remember, airflow, as air flows, let's say from inside to outside in the winter, it will carry with it heat and moisture. In the summer, if it's coming from the outdoors, again, it's carrying with it heat and moisture to a new location that might be cooler and can create challenges, condensation, and other issues. Airflow was, we could deal with it when there wasn't lots of insulation. It's back to that original concept of the 4 control layers and their order. But as we added significant insulation in the 70s and 80s and 90s, it became clear we simply could not tolerate airflow across these permeable insulation systems, moving moisture to the cold side of the insulation. Just was not going to work, was not acceptable, and led to a lot of failures. So today, we simply have to stop the airflow, which means we're stopping the moisture wetting potential across the insulation scheme. We are stopping heat loss, which is air leakage out of a building is a huge fraction of the total heat load, heat loss or heat load of a building. So it's doing a lot of good things for us. It is also, though, removing a powerful drying mechanism when conditions might be appropriate for drying out those materials. So what that's leading up to is we're going to have to replace that with vapor diffusion drying. Again, primary driver is air pressure, and by all means, we should be managing those pressures. We don't want to run a building in a cold climate under a strong positive pressure in the winter, pushing moisture out through any holes or leaks that are left. We don't want to be running negative pressure in the summer and drawing copious amounts of outdoor humidity into our building enclosure or into our building. So by all means, we should be managing and controlling those pressures across our thermal or across our air boundary, our building enclosure, if you will. Absolutely essential. So here's kind of a theoretical framework drawn from the commercial side of things, and it lists basically targets for air leaks through a material, a single material. It could be a piece of plywood, it could be a piece of foam insulation, whatever. Then at the assembly level, you think of it as kind of the wall assembly of layers. What might be appropriate leakage across that due to some of the installation and execution and construction joinery, if you will. And then what should the air leakage be for the entire building? It's going to include all of your different assemblies around the entire building enclosure. I'm going to move on and kind of put this in context of kind of what we think of as residential. Again, typically it's measured at the whole building level in air changes per hour at 50 pascals of pressure, blower door test essentially. And our current code is 3 air changes per hour. The Zero Energy Ready Home program is 2 air changes per hour. And if you're really trying to achieve net zero energy or beyond, certainly 1 air change per hour is a very appropriate target. So where does the air control layer belong? Inside, outside, in between, or both? This is really a bit of a theoretical question. If you all can picture taking a shoebox, taping it all up, make sure there's no other holes, and then cutting a hole, let's say, in the lid, and then trying to blow air into the shoebox, it won't happen. So that shoebox could be facing inward with a hole, it could be facing outward with a hole, and there'd be no flow across the hole. So that says the air barrier can be anywhere. That's true. But there can't be any other holes in the shoebox. So what happens in real buildings is frequently there are holes, let's say at the top plate or the bottom plate, so that air might move in through that hole and then out vertically or even horizontally perhaps, even though the outside might be perfectly airtight. That's going to allow indoor air, let's say, to move into the wall cavity. That's not a good situation. So what's frequently happened here is in colder climates, we've thought about the air barrier being on the inside, and in warmer climates, we've focused on the air barrier being on the outside. But that's not required. I just want to make sure people are clear. It makes sense, but it can be done in any location if we're being very, very careful about all sides of the box, so to speak. So the real point is, in the end, it's all about continuity. This is continuity and air tightness. It must be continuous and it must be air sealed. So again, we come back to the pen test for air. We used red for energy or heat in the first pen test. We used blue for water in the second pen test. So now we're going to use purple because air moves both heat and water vapor for the air layer. Again, you can do this on a section view, a plan view, a detail, any of your construction details, your connections between roof and wall or wall and foundation, your window details. Again, look at them, explicitly for the idea of what is my air control layer, or it may be layers. How is it continuous from one component to the next to the next? Very, very powerful concept, very simple to do. You can sit there, whether it's at the drafting table or on your computer, and look at that in quite explicit detail to make sure you've addressed all the potential connections and ensured continuity and integrity of your air control layer. Finally, vapor control layer. So this one's going to be a little tougher. It's a little more challenging. It's a little more ethereal, if you will. So the intent is to control vapor diffusion caused by vapor pressure gradient from inside to outside. As I mentioned, in almost all cases, in cold weather, winter weather, there's going to be a vapor pressure gradient from indoors to outdoors. And certainly if you're air conditioning your building in a humid climate or slightly elevated, hot, humid climate, there's going to be a vapor pressure inward. And then if your cladding is very, very wet and the sun's hitting your cladding, there's going to be a massive vapor pressure gradient from your cladding system pressing inward on your building in the summer. So again, the vapor pressure can and should be managed. In that last example, we provide venting or drying behind the cladding so that that vapor pressure can be relieved to the outdoors rather than being concentrated and pushed back through your building enclosure layers or the building enclosure system. Again, it's a slower mechanism overall, as we talked about earlier, and it may not seem as critical, but it simply can't be ignored as a concern for wetting in very cold climates, in very hot humid climates, or in high humidity environments. Secondarily, it can't be ignored because it does provide the drying mechanism. So this is going to be our inherent challenge here, is to slow down the wetting and yet allow some drying to occur. And that's where the control air concept is going to be played out here in just a few more slides. So again, as insulation increases, the vapor permeance has to go down. There's less heat flow, there's less energy available to keep vapor as a vapor. And so again, and the folks that are trying to achieve these very high R values, you just have to recognize that vapor control has to be in play. Again, with air conditioning, for most climates today and most places, people are air conditioning as well as heating, where you again have significant heating and significant air conditioning. You're going to have to manage vapor from both directions. It's not unidirectional any longer. So that adds a lot of complexity to the problem and adds to some of the new strategies, if you will, for the perfect wall. And remember, if it gets wet, the only drying potential we generally have is vapor diffusion. So we have to have a clear way for that vapor to escape. And you'll see that play out in the coming slides. Different levels of permeability. I'm not going to go into the detail here again, but we typically have these definitions of classes of vapor permeance, if you will, in the codes. 0.1 to 1 perm is typically what's required in many of our codes, 1 perm or less. And there are many climates that have been using plastic, for instance, polyethylene as a vapor retarder, which is a class 1.1. I'll comment on that as well. So most building codes require a class 1 or 2, 1 perm or less on the warm side in winter. Again, you can see that the codes are still biased a bit towards winter northern construction, heating dominated buildings. And so that comes into play here. Conversely, the code doesn't really address the exterior vapor retarder concern for summer conditions where we have a high outdoor vapor pressure wanting to move inward. And so we'll talk more about that, but you basically have to protect, again, in buildings that have significant heating and significant cooling, you're going to have to deal with both. One's pretty easy to achieve. Lots and lots of things out there, things that are historic, such as craft face paper, bats, are there. Newer materials such as a smart vapor retarder. Also interesting to note, OSB, a 1/2-inch OSB, dry cup is 1 perm. So in fact, we have been using exterior vapor retarders in our buildings for some time here in the sheathing choice that we have. That might work in some places. It might also cause challenges in others. Also, I want to just remind folks that 0.1, a true vapor retarder, vapor barrier almost we could suggest here, is a very tricky number. It certainly is lower than we need to prevent wetting. It can be safe if it's placed in the right location, and you'll see some here in the future where they, in fact, are using very low perm materials safely. But ultimately, the material surface must be warm enough to prevent condensation. So in the end, this is a strategy. It's a way of thinking about the wall system. I'm using walls in this case. Is there a proper vapor throttle to prevent vapor wetting of moisture susceptible materials in both directions? And secondarily, if a moisture susceptible material gets wet, have we provided a clear drying potential or direction for it? So buildings get wet, outside in, inside out. Things do get wet due to some imperfection in our design, execution, or operation. So how are moisture susceptible materials protected in the first place? And secondarily, how are we going to provide a drying potential for those materials should they get wet? Again, it's generally outward in the winter, inward in the summer, except below grade. So here's the point. Have we really hit the end of the road with the 2x6 cavity insulated wall? And my bias is yes. Cavity insulation just creates a lot of very challenging situations, especially as we increase the R value of that insulation. And in particular, if we're using air permeable, vapor permeable insulation. So again, if we're using spray foam and some other techniques, yes, this story changes a bit. But kind of the traditional scheme of cavity insulation, we do that because we can use cheap, less expensive insulation materials to get a high R value, but it challenges the system. In general, I think the R values are too little. Once we get the R values up to where they need to be, the exterior is too cold in the winter and the interior is too cold in the summer relative to the vapor and air transport across this air permeable, vapor permeable insulation. It's incredibly risky. In the end, what you have to do is have a two-sided wall. You have to protect both sides of the wall. And that requires high level of execution. And even if it's done very well and we have an accident in the future, the drying potential is simply too little to protect all of our susceptible building materials, the insulation, the framing, etc. So this gets worse if we don't have perfect bulk water control. It gets worse if we don't have cladding that's properly drained and vented. And it gets worse if we have significant air conditioning use across longer operation with lower indoor temperatures and RHs. So I'm going to quit there just very quickly to see if there's any quick questions that popped up on the control layers, and then we'll move into the perfect wall and our case studies. Have you seen anything?
Yeah, so the question was, how does vapor pressure act when there is a hole in the air barrier?
Perfect question. So if we have a hole and there is no flow, air flow across that hole, because there isn't a second hole in the wall, right? Back to my box. So if we had a box, that shoe box with a hole in it, and even if there was an air pressure, there'd be no flow of air from the house side into that hole, let's say, or into the cavity. However, there would still be vapor diffusion through the hole. So there is vapor diffusion through air, there's vapor diffusion through a hole. That can be calculated, and it's simply how quickly do the water vapor molecules find that hole and move through. And again, if it's a very small hole, we're talking about a nail or a screw or something like that, it's pretty much insignificant. If it's the size of a electrical outlet box in a very, very cold climate with a very, very cold sheathing, then that diffusion could be potentially concerning or contribute to enough condensation to be of concern to us. But generally, the bigger problem is their air is leaking across that outlet box. Now we have both diffusion through the air, if you will, around the box, and actual convective mass transport of air through the leak of the electro box, moving even greater quantities of water into the cavity.
And then the last question before we move on is, I think the question is posed, for cold weather air pressure control, can you operate exhaust fans or one fan to reduce stack pressure in a tight building?
Yeah, so yes, and that's actually how old buildings worked. Old buildings had big chimneys. They used a lot of air, threw a lot of air up the chimney, especially when it was cold and the furnace was working hard. And that basically put the building under negative pressure, drawing in cold, dry air, moving inward. As it warmed, its potential to pick up moisture increases actually, and it would dry the building enclosure. So that was a protective mechanism we had in the old days when the house ran negative and the walls were leaky. In tight homes, one could potentially do this same technique with an exhaust fan, if you will. You just have to be careful because you're also going to draw in soil gases that could include radon from below grade. You might have an attached garage where you're drawing in garage gases. So putting a building under an intentional negative pressure in the winter might be good for the building enclosure. It might not be good for your indoor air quality. So clearly it's a great point, and it's one where I think we need to spend a lot more time thinking about how we actively control the pressure in our buildings for high performance. Good question.